we discussed already that you can reduce harmonic oscillators in any dimension to essentially one-dimensional problems by separation of variables. We also discussed how to use smart dimensionless variables in such a way that all constants appear as if they were put to 1, okay? And the end result of our study is that the Hamiltonian of this harmonic oscillator could be written as h bar omega divided by 2, then the dimensionless momentum square plus the dimensionless position square, okay? So essentially as if here I have just one half, no mass, no omega, nothing, okay? Obviously remember that this x and p, now their commutator is equal to I. Indeed, p in position representation is equal to minus I, the derivative, no h bar, okay? Good. We'd like to solve this. So to solve the Schrödinger problem associated to this harmonic oscillator, but rather than writing the differential equation, which usually is associated to a Schrödinger time-independent Schrödinger equation, I proceed in a slightly different way. Okay? I define a new operator, which I call A, which is given by 1 over square root of 2 x plus IP. Notice, this is not an emission operator, right? You see, x is emission, p is emission, but this is x plus IP, okay? So if I ask you to calculate the emission conjugate, you will tell me immediately, no, that is x minus IP, right? Very good. Now, they appear very strange, but they are not that strange, because remember that IP, okay, IP is equal to the derivative with respect to x in some sense, right? So in practice, this as a differential operator is x plus the derivative with respect to x, okay? And this is simply x minus the derivative with respect to x. Is it clear? Well, they are not particularly strange. They're not emission, but they're not infinitely strange. Okay. The nice thing is, obviously, you can invert these two equations, okay, and determine x in terms of A and P in terms of A and A dagger, obviously. You see, if you sum the two, okay, the P disappears and you get 2 divided by square root of 2x. So you determine immediately that x is equal to 1 over square root of 2. The sum of A plus A dagger. Is it clear? Should I do the algebra more explicitly? Should it? No, it's okay, right?
Yeah, it's okay.
Yeah, good. Now, take the difference between this and that, okay? Now this disappears. I do the algebra here. So A minus A dagger, okay, is equal to 1 over square root of 2. This goes away. I get I from here, P, and then I get plus IP, so 2IP, okay? So I get essentially square root of 2IP, and therefore, if I just invert for P, P is equal to, let me write it, P, 1 over square root of 2I, A minus A dagger, okay? Very good. Now that I have this formula, I can put them in the Hamiltonian, okay? And in fact, for me, the Hamiltonian, okay, is simply this. This is just a factor, it's the energy, h bar omega. If you want, I could define this object here to be simply, let me write it like this, p squared over 2 plus x squared over 2. Okay? It's the Hamiltonian divided by h bar omega. Now, let's see what is x squared over 2 and what is p squared over 2. I use this formula. Okay? So s squared is equal to 1 over over 2, okay? And then I have A plus A dagger times A plus A dagger. I will put the heads, they are operators, obviously. And you have to remember that this is like a square of a binomial, but you don't do it by disregarding the order, because these are operators. So it's important to keep track of the order. So I have 1/2 A squared plus A dagger squared plus A dagger plus A dagger A. Okay? You see, the order of these two things is different. But now, let's look a little bit. Remember that this is the commutator. Let's define, let's see what is the commutator of A and A dagger. Okay? This is equal to, let's see, A is 1 over square root of 2 x plus IP, and the other is 1 over square root of 2, so square, x minus IP. Okay? So let's calculate these commutators. This is 1/2, then x commutes with x, p commutes with p, so the only two terms are this with that, and this with that. Now, x commutator p is I times minus I is 1, okay? So this is 1. And this term is p commutator x, which is minus I times I, another one, plus 1. Okay, so this is 1. So the commutator of A and A dagger is equal to 1, which means in practice the following: A dagger minus A dagger A is 1. 1 means the identity, obviously, as an operator, right? I write it as 1, but you could view it as an operator. Okay, so whenever I have A dagger or A dagger A, I can trade for the other, okay? So for instance here, I might use the fact that this object here, A dagger, is equal to 1 plus A dagger A, which is this. But let's leave it for a while, okay? Then I have p squared, okay? What is this? 1/2. But there is a minus 1 this time because there is an I there, okay? So minus 1/2. And then I have A minus A dagger times A minus A dagger. Very, very similar calculation except for the minus here. Let's see, equal to minus 1/2. The A square and the A dagger square are untouched. So A square, A dagger square, okay? The other two gets an extra minus sign, but remember that there is also this, okay? So let me write it like this: minus A dagger minus A dagger A. Is it clear so far? Okay, now I want to sum these two, okay? The sum of x squared plus p squared. Let's see what survives. You see that this with this cancels, right? This with this cancels, okay? What about this? No, this has plus, and this also has plus. So in fact, the sum of these two things is equal to the 1/2 and the 1/2 give me 1 is given by A dagger plus A dagger A, right? Is it all right? Now, using this fact, I can also rewrite this as 1 plus A dagger A. So this is also equal twice A dagger A plus 1. Is it clear? So this is what I just derived. The Hamiltonian, or the piece of the Hamiltonian, this important is twice A dagger A plus 1. Okay, but remember that there is a factor 1/2. So I copy it here, and this is A dagger A plus 1/2. Okay? A very nice formula. Okay, you might say, well, you have done just some algebra. All right. Now, let's start to see. Remember, this is a problem where there is a potential like this, okay? So the minimum of the potential is in 0 here, okay? And its value is 0. So the spectrum of this problem is non-negative, okay? Let's start to look for the ground state. Okay, so you see immediately there is a plus 1/2 here, times something. You might think, well, maybe this something can reduce the energy. Well, not really. Okay, let me first do one consideration, okay? Suppose for a second, that I have found a state, phi 0, let me call it phi 0 of x, such that when I apply A to it, okay, I get 0. Okay, is this something strange to you?
No.
Not really, okay? Look at the expression for A. This means, in practice, 1 over square root of 2, x plus the derivative of x of phi 0 of x should be equal to 0. What type of differential equation this implies for phi 0? It implies the fact that the derivative with respect to x of phi 0 is equal to minus x times phi 0. Okay? So what is the solution of this differential equation?
Gaussian.
It is a Gaussian, in the sense that if you take phi 0 of x equal to some constant times e to the minus x squared divided by 2, when you take the derivative of this, you bring down a factor minus x, right? Because remember there is x squared, so it is x and the 2 cancel this 2 from the derivative. So this is in fact satisfied, okay? And you can select the C in order to normalize the thing. So in some sense this is a state, okay, which is a Gaussian, centered in 0, okay, which I draw like this. Notice, remember, this is x, which is big X divided by the oscillator length, okay? So I can ask you how much is the wave function at, say, 32 angstroms, and you would know how to calculate it. Okay, good. Now, what is the role of this thing? It's a function without modes, such that A kills it. Let's see what happens if I apply the Hamiltonian to phi 0. Okay? Well, what happens is the following. First of all, there is h bar omega in front of everything. Then there is A dagger A, okay, plus 1/2 applied to phi 0. Okay? Now, the 1/2 is just 1/2 times the identity, no problem. But when A acts on phi 0, you get 0. Okay? So the result of this is simply h bar omega divided by 2 phi 0 of x. So I have discovered that this is an eigenstate, okay, with eigenvalue h bar omega over 2, okay, which means here, okay, somewhere, this is h bar omega divided by 2. All right? No, you might be suspicious. Is this the ground state? Or maybe not. Well, you see, it has no nodes, okay? So you remember that as you go up in the spectrum, which I anticipate for you will be a discrete spectrum with equidistant levels, all separated from each other by h bar omega, okay? This is anticipation of what will come. As you go up, you get nodes, right? And also notice this is an even function. The first excited state will be odd, the second will be even again with no nodes. So you suspect that this is the ground state. But if I ask you, please prove, okay, that this must be the ground state, then the strategy is the following. I use the variational theorem. The variational theorem, I don't know if we have discussed or you have seen it somewhere, tells you the following thing. If I have a state, any state phi, okay, and I calculate the expectation value of the Hamiltonian on this state, and suppose that the state is normalized, so phi is equal to 1, then this object is greater or equal to the ground state energy. Okay? Do you know how to prove this? Have you seen it before? Or is it the first time? Seen. Okay. The proof is not difficult. In case, try. If you don't succeed, let's discuss. Okay? Now, let's see if we can calculate this quantity, okay, for phi0. For phi0, the situation is very simple because phi0 is in fact an eigenstate, okay? So this is equal to h bar omega over 2 times phi0. And since this is normalized, the result is h bar omega over 2. Okay? So you know that the ground state cannot be larger than h bar omega, because I have found a state with an eigenvalue h bar omega over 2. So it cannot be larger than this. So this must be greater or equal to the ground state. But I want to somehow argue that somehow this is also the minimum. Let's see why. Let's consider this quantity here. So it is equal to, I will write it again, phi, then I have h bar omega, then I have a dagger a plus 1/2. This is the Hamiltonian phi, right? This is this quantity here. Is it clear? Okay, good. One term is this 1/2 here. So it is equal to h bar omega over 2, right? It comes from this term, 1/2 times that, and then phi and phi is 1. Okay, plus h bar omega over 2, no, sorry, h bar omega times phi a dagger a phi. Okay, again, I could use the notation in which I don't put this or I put the rack. Okay, never mind. Let's not put it, in fact. Okay, these are two operators acting on phi. And then I take the scalar product with that. Now you know that I can bring this object to the left-hand side, okay, by transforming into its emission conjugate. And the emission conjugate of the emission conjugate is the operator itself. Okay? So this quantity here is equal to h bar omega times A applied to phi, scalar product with A applied to phi. But this quantity here is what? Is the norm, the length of the vector A phi. Okay? I can write this as h bar omega, the length of A phi, okay, modulo squared. All right? So this quantity here is by definition greater or equal to 0. So you see that the ground state energy, which I have somehow here, should be h bar omega plus also some positive thing. So the minimum, in fact, is when this term is exactly equal to 0. And is equal to 0 precisely when A applied to phi is equal to 0. So indeed, what we just guessed at the beginning is the ground state. Okay? Any other state should have larger energy. Okay? So please revise this very, very simple argument, but make sure you understand clearly the story. Okay?
So
yeah.
basically, you prove by the norm that by taking the norm 0, you prove that the ground state is h bar omega over 2.
Yes, yes, exactly. So in some sense, I have evaluated. This is the left-hand side. Okay, is equal to this. It is equal to this plus something. Okay, so the minimum. So the minimum that this quantity can have over states. So I should write it like this. This is the minimum of over states that are normalized, okay, of this quantity. I just explained to you is equal to h bar omega over 2, because any other extra term is non-negative. Okay? And since I already found a solution for which this quantity is equal to h bar omega over 2, that is the solution. Okay? The ground state. Good. Let's continue. So I found the ground state, phi 0, which is this nice Gaussian function. And the E0, the ground state energy, is h bar omega over 2. Now I want to construct all other states. Okay? And here comes a little bit of algebra now. Okay. Good. I can erase this. And I can erase this. Okay. So phi 0 of x is equal to constant e to the minus x squared divided by. Okay, let's proceed. Suppose I take a state now phi 1 of x, which is equal to a dagger applied to phi 0. Okay? So this time I do not apply a. If I apply a to phi 0, I get 0. And that's the end of the story. I apply a dagger. By the way, the name of these two guys is distraction operator and creation operator. Okay? You will use it also in second quantization for bosonic particles. Okay? In fact, the algebra is identical. Okay? Including the commutation relationship, obviously. Okay? So this is one of the reasons for theory to really say how useful it is, this approach. Not only solves the harmonic oscillator, but in fact lets you practice with the second quantization formalism for boson. Okay? Good. So phi 1, I can calculate what it is, because a dagger, remember, is equal to this. So this object, just to be definite, is 1 over square root of 2 x minus the derivative this time, okay, times phi 0, which is constant, times e to the minus x squared over 2. Let's calculate it, just to make acquaintance with this object. So this is c divided by square root of 2, okay? Then I have x, okay, that's nothing. And then I have minus the derivative applied to this. But remember that the derivative brings down minus x, okay? Good. Times e to the minus x squared over 2. So this is 2x now. And the factor square root of 2 gives me equal to square root of 2 times c times x e to the minus x squared over 2. So it's the same Gaussian, but this time multiplied by a factor x, which means something like this. Okay, so it's a linear term, so it is 0 in the origin, and then does something like this. Okay, so it's still Gaussian here in the tail, but is negative here. Okay, it's very small and ugly to see, but hopefully it's clear. In the tail, it's a bit above the Gaussian that I have, but essentially Gaussian. But here in the middle, it's linear. Okay, so any polynomial times a Gaussian will have oscillations here, and in the end, the tails will go to 0 exponentially fast. In fact, Gaussian fast. Is it clear? So this is the state. Now you might say, so what? What do I do with the state? I will prove to you that this is in fact an eigenstate of this Hamiltonian. Okay? let's show it. Okay? So let's consider now H applied to this phi 1. Okay? So phi 1. Now, this is equal to h bar omega over 2, a dagger a plus 1/2, No, sorry. H bar omega. H bar omega. Like this. Okay? Apply to phi 1. Okay, let's calculate. So it is one term is h bar omega over 2, right? Good, times phi 1. Plus, now let's see. A dagger, so sorry, h bar omega in front, and then I have a dagger times a, and then I have phi 1. Notice that phi 1 is a dagger phi 0, right? This is by definition my phi 1. Now you have here a situation where, how do I calculate this? It would be very nice if A was acting on phi 0, because I was getting 0. But, so A, remember, is a distraction operator, is the killer, okay? Once A comes close to phi 0, everything, poof, goes away. But A dagger here acts like a bodyguard, okay? So there is something that protects phi 0. And what you want to do is to go over the bodyguard, and you can do that because you remember that I can always rewrite the fact that A dagger is equal to 1 plus A dagger A. Here you see the killer is now to the right, but there is a price to pay, 1, okay? So let's use this, and I rewrite this as h bar omega A dagger, okay? This is 1 plus A dagger A, this part, and then I have phi 0. Let's look at this expression. There are two terms. One is the 1, that's simple, and the other term is A dagger A applied to phi 0, and then there is another A dagger further to the left. But this already, you realize, gives you 0, okay? The killer is now in position, okay? So you get 0 from this. Good. So the only remaining term is this, which I write here. So it's h bar omega A dagger times phi 0. But A dagger times phi 0 is by definition my phi 1, okay? So this is equal to h bar omega phi 1, okay? So end of the long story, this object, if I erase everything, well, I better write it here, is h bar omega over 2 times phi 1 plus h bar omega times phi 1. Okay? So I can sum these two things, and what I get is 3/2 h bar omega times phi 1. I produce for you a state which is an eigenstate, and whose value is not 1/2 here, but 3/2. So suppose that here I plot the energies divided by h bar omega. So the first one here would be at 1/2. The second is separated by exactly 1, and is, sorry, here, and is at 3/2. Okay? Certainly an eigenstate. Okay? In fact, you realize that it has all the features that you would suppose from the first excited state. It has 1, 0, exactly in the middle, and it is odd. Okay? Now the procedure can be repeated. Okay? And the story goes roughly as follows. You have to practice a little bit with this commutator of things. Okay? After a while you get athletic. And this very similar story can be repeated. Now, let me just introduce an important object, which is this quantity here, A dagger A. Okay? This quantity, A dagger A, which appears in the Hamiltonian, I will give it a name. I will call it N. Okay? And later on, I'll show you that this is a number operator, so it counts something. What it counts? It counts the following thing. Let's define the states. Phi n, n is an integer now, could be 0, 1, 2, okay? Of that, which is equal to a certain number of operators A dagger precisely n operators A dagger apply to phi 0. Okay, remember, do not apply A. Apply A dagger, because otherwise you get 0. N of them. So for n equals 0, nothing, just phi 0. For n equal 1, the state I've just constructed. For n equal 2, put 2 A daggers there. Okay? The thing that I want to convince you is that this object here are eigenstates of this operator. In other words, if I apply n, which is A dagger A, is a shorthand for a 2 phi n tilde of x, what I get is precisely n times phi tilde n of x. You might wonder, why do I put a tilde there? Because nobody guarantees that these states are actually correctly normalized. Okay? We will see the normalization issue later on. For the time being, let's forget about normalization. Okay? So this is a very important relationship because it immediately tells you, if I use it, that h applied to phi n tilde, how much it is? It is equal to h bar omega A dagger A plus 1/2 applied to phi tilde n. But this is precisely the operator n that I was mentioning before. And this operator is such that counts how many A daggers you have applied there, okay, and gives you back n. So the result of this calculation is simply by using this equation, n plus 1/2. Now this is now a number, not the number operator, okay, but just an integer times phi tilde n. Okay, so in other words, phi tilde n, if this is true, which we have to verify, it's an eigenstate with eigenvalue n plus 1/2. So in other words, it's one of the states here in the ladder, n steps above the ground state. Okay? Okay. Let's see how this comes. It is a bit of a game of commutators that you have to play. By the way, n application of these operators bring down factor x and derivatives of this polynomial in front. So you realize that what you get is a generic polynomial, and if you think a little bit, you will realize it's a polynomial of degree n. Okay? So this object here, if I try to write it explicitly, is essentially some polynomial of degree n times the Gaussian. Now I write it Hn, not because it's a Hamiltonian, but because it's Hermite polynomials. These are Hermite polynomials, okay? So they are usually denoted with the Hn, okay? Never mind for the details. Try to calculate the first 2 or 3, okay? So try to calculate phi tilde 2 and phi tilde 3, for instance. And you will see what comes out by applying twice these operators, or 3 times this operator to the Gaussian, is precisely the Hermite polynomial of degree 2 and 3. But this is just to do a little bit of gymnastics. To prove the general statement, what I should do is the following. Okay. As you see here, there is a situation where I have let's look at this, because this eliminates a lot of concepts. So I want to prove that A dagger A, which is the n operator, acting on the state phi tilde n, which is A dagger n phi 0, okay? This object is simple. I want to convince you that this is equal to m times A dagger n phi 0. Okay? This is the statement that is written upstairs here, okay? Just translate it into explicit formulas. All right, how do you show that this is true? Well, again, the trick is that A would like to stay close to phi 0 to kill phi 0, right? But there are now n bodyguards, n of them, and I have to go through all of them. how much will it cost? Okay? The answer is going through a single bodyguard, you have to pay $1. Going through n bodyguards, $n. Okay? Or euros, you decide here euros. Okay, good. Let's show this. The proof of this is the following. Suppose that I ask you, what is the commutator of A with A dagger? You tell me, well, it's Schwarz, right? I now ask you, what is the commutator of A with A dagger to the power n? Okay? Now, you might say, I don't know. Okay, correct. Try to invent a recursive proof, okay? You remember that when you have A commutator B, C, okay, you know how to write A commutator B times C plus B commutator, okay? Remember the formula. Let me write it. A, B, C plus B, A, C, okay? You use this kind of formulas. Huh?
In this case, do we have to make it A dagger, then A dagger?
Well, you write this as A dagger times A dagger to the minus 1.
Oh, yeah.
Okay? And now you have to invent a formula or prove that the result is in fact equal to n times A dagger to the n minus 1. Okay? So, prove by induction using the formula that I give you. I mean, this is certainly true for n equal 1, right? Because this is just A dagger to the 0, 1. Okay? Now, show that if it is true for n, then it is true for n plus 1 by just using the formula that I give. Okay? And this provides for you a nice inductive proof that this is true for any n. Now, if it is true for any n, then I can use it, and I can say that A dagger n, every time I find this thing, then I can substitute it with n, A dagger to the power n minus 1, plus the reverse thing, so A dagger to the power n times A. But this is a nice thing, because now I have gone through the bodyguards, and A applied to phi 0 gives me 0. Okay? So when I apply this object to, so the situation that I have in mind is this. Okay? So try to apply this kind of formula there. So you see that I apply it to phi 0, I apply here to phi 0, I apply here to phi 0, and this gives me 0. So the end result is that this object, okay, is equal to A dagger, the first one. Then this thing is equal to this, so it's equal to n times A dagger to the power n minus 1 times phi 0. And this is just vanishing. Then I see that these two things go together. This is a number, so this is equal to n times A dagger to the power n again. You see, 1 plus n minus 1 is 0. Okay? And this is precisely what I wrote before. Okay? So, believe me, the crucial ingredient is this, okay? Which you can prove by induction. Good. So, these are indeed nice eigenstates of the Hamiltonian. Now, the question is normalization. You will realize that the normalization is not right. And in fact, the normalization requires a little bit of work, more work. Okay, I'll ask you now to prove the following thing. Where should I write it? Here. So I will ask you to prove that phi tilde n as written, okay, so with no constant effort, just n application of A dagger, phi tilde n is equal to n factorial. Okay? And the way, well, this is an exercise, so I ask you to try, okay? And again, a way to prove is the following. Remember, this is, say, A dagger, n of them, apply to phi 0. And here I have the same thing, but on the graph, so I have essentially phi 0, and I can bring them here as n of them, okay? So I have n A's and n A daggers, okay? In between phi 0 and phi 0, okay? Now there is a situation where this A would like to go there to kill phi 0. It has to pay some numbers. Then there is another A, a second killer, that would like to go there, and it has to pay numbers, okay? Try to count what is the number of plus ones that you get through.
First one with n, second one with n minus 1.
Yes, this is roughly the ADR, and you get n factorial. But try to prove it, okay? There are some suggestions in the exercise. I think that the commutator, this commutator here is again useful. Okay?
Sorry, is that a commutator? The one?
Huh?
That one? That formula. A dagger and...
This is a commutator.
No, the one here.
Where?
The...
Here?
Yeah.
No, this is just, well, it is a commutator in the sense that I wrote this as a dagger to the power n minus a dagger to the power n a equal to n a dagger to the power n minus 1. So I wrote this to the right, you see? I'm simply making the commutator explicit by just bringing it to the right hand side. You see, this was brought here, and then I apply phi 0 to every term.
And then the one you asked to prove is the commutator.
What?
You asked us to prove the commutator, or it's already...
Oh, yeah, well, this is the first proof. Proof by induction, by mathematical induction, that this is true. Okay? So prove this first. With this, you can get very, very easily the result I wrote there. Okay? Now I ask you, using this, to prove a slightly more complicated thing, which is that when you have n objects and n A daggers, okay? So the process of commuting this with this gives you n factorial. Try it. Okay? Maybe you try first with 3, okay? Make it explicit and then try to understand the idea and prove it. Okay? Good. Now, if this matrix element is n factorial, means that phi tilde is not normalized, right? So, can I ask you, how would you normalize? So what is the state phi n that you would write to get the result normalized? Right? Divide by 1 over square root of n factorial. Okay? So these are the states that I would write to have them properly normalized. Okay? So with this factor 1 over square root of n factorial, you are done. These have all norm 1. Okay? Good. Now there is one last thing that I would like to do, which is the following, which is to deduce for you what this A dagger and A do. So I will try to prove to you that A dagger lets you go up in the ladder. So again, here I have a state phi 0, here I have a state phi 1, here I have a state phi 2, okay, and so on and so forth, for all integers. A dagger lets you go up in the ladder, A, the destruction, gets you down in the ladder. In other words, I want to show to you that A dagger applied to the state phi n is equal to the square root of n plus 1 times phi n plus 1. Okay? Notice, it's not just 1 times the thing. Okay? And why? Let's see why. You see, this object here is equal to a dagger. Then this is a dagger to the power n divided by square root of n factorial times phi 0. Okay? So immediately you notice that this is like a dagger to the n plus 1, but it's not correctly normalized. So I write it as a dagger to the power n plus 1. Now I would like to have here the square root of n plus 1 factorial. Let's put it. What did I put more? I mean, there was no n plus 1, so I have to include here an extra square root of n plus 1, right? In this way, the two things are absolutely the same. And now I read that this is phi n plus 1, and I am done. Okay? So there is an extra square root factor that you have to pay if you want this space to be correctly normalized. Okay? And in the same way, you can prove this other equality, which is the fact that A applied to phi n is equal to square root of n times phi n minus 1. So, you see immediately, a dagger applied to phi n lets you increase the n by 1. Okay, so it's the ladder operator going up. This is a factor square root of n plus 1, to pay attention. A lets you decrease it with the factor square root of n. In particular, notice, if I apply to phi 0, A applied to phi 0 is equal to the square root of 0, 0. Okay? So you recover the original thing we started from, the fact that phi 0 was distracted, was annihilated, as you say, from the distraction operator. A. Is it clear? Good. This is the tower or the ladder of states of the harmonic oscillator. Okay? You know now the energies and you know the states, and they are constructed by applying a dagger operator repeatedly and paying attention to the normalization. Is it clear? Now, notation. Very often, rather than writing this thing, first of all, yeah.
In this case, A applied to phi 0 equal to 0 because also we haven't phi minus 1.
Correct. There is no need for phi minus 1 because the factor here is 0. So you do not ever invoke. Okay? You just phi 0 is enough. Phi minus 1 is never attached. Okay. Yeah.
What if we start the A with phi minus 1, and then we will have some complex.
Why do you want to start? I mean, I write this equation for n equal to 0, 1, okay? So you never start from minus 1. No, do not overdo it, okay? And this equation is also true for n equals 0, 1, 2, okay? Good. Notation. Okay. Notation is the following. Sometimes we will find, so far I was very slow, I was writing something like this. Sometimes you will find this written as a cat, like this. In a second we will understand what it means. Okay? More precisely, this would be this object, really. Okay? We'll see in a second. Just any part of the lecture will be devoted to this. So, this is one possible notation. Sometimes, rather than this, you find n. Okay? Obviously, phi 0 has a similar destiny. Sometimes you find it to be 0. Okay? And this state in particular is a name. It's called the vacuum. Okay? Don't think that there is nothing. There is somehow a wave function, which is the Gaussian. Okay? This is the vacuum of the excitations. Okay? So somehow there are no excitations there because this is the ground state. Okay? And all the other states are progressively filled with excitation by applying a dagger. So a dagger does not create particles. There is only one particle. It's our object with mass m and frequency m. But you increase the excitations. Okay? Now, obviously, when you will do Formans, for instance, you will see that this describes the situation where the solid vibrates more and more, okay? Although the number of ions in the solid are always fixed, okay? So don't be confused by the fact that here you change the number of excitation. You don't change the number of particles, you change the number of excitations when you go up in energy, okay? This is, by the way, precisely the same formulas that you use for photons. Okay, photons are excitations of the electromagnetic field. And the formulas that we wrote is precisely a Planck formula. Okay, the energy of the single mode of the field described by this A and A dagger is n times h bar omega. Okay, you see it essentially here. Okay, so this is Planck, n times h bar omega. I can have no photons, okay, or 1, or 2, or 3, okay, in the same field mode. Packets. So this is precisely our first lecture starting point. All right, is it reasonably clear? And this is, by the way, figures for reference of the first few excited states of this problem. Look on the here. Ground state, first excited state, second excited state, third excited state. More and more, look at the 20th excited state. This is the modulo square, by the way. So there are negative sign, blah, 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 but then you take the modulo square. You see lots of zeros, but nicely, something that emerges is that one over square root thing. So the probability of finding a particle is more and more closer to these boundaries. And you realize that this approaches the classical limit, where you have a classical oscillator. Since the oscillator will do something like it stays more at the boundaries.
Yeah.
It is faster here, and therefore the probability to find the particle is higher at the boundaries. This emerges in the limit of very, very large quantum numbers. Okay? And in fact, this is the classical probability, and there is a small exercise to actually show that this is the classical probability. Okay? So, good. Let's end. There are a few exercises, elaborate, but very, very useful. Exercise 3.7 and 3.8. They explain things about harmonic oscillator. In particular, you can practice with the concept of a coherent state. Very, very, very important in quantum optics. Okay, so you would not be able to do quantum optics without first doing this exercise. Okay, which is an harmonic oscillator exercise. So you see the connection between a very elementary exercise like this and a very important concept in optics. Okay, good. Now I will quit the harmonic oscillator here and start with chapter 4 of our story, which is a bit now a change of gear, in the sense that I will now try to reformulate in a slightly more abstract way. I mean, don't think that I will do tremendous abstract formulas, but I will try to tell you a little bit more about Hilbert spaces, what it means to change representation and so on and so forth. Why do you sometimes write wave functions, sometimes you write cats? These things I have repeatedly kind of alluded at, but never really devoted some here. Okay? Let's try to do it. I prefer not to do it at the beginning because I want you to familiarize with simple concept, a wave function, okay? Rather than a very, very abstract concept. Now, so far, essentially, we dealt with the Hilbert space, okay, H, or as a linear vector space of functions, okay? This was a linear vector space of functions. Okay? So I know given two elements, psi and phi, in this space, how to calculate the scalar product of them. We define already the scalar product to be something like this. You integrate over all x, the psi star of x times phi of x. Okay? This is our definition of scalar product, and from this you can calculate the length of a vector, the distance between two vectors, and so on and so forth, because from the norm you define the length, and therefore the distance. Now, but in principle, any complex linear space is okay. Okay, so think, for instance, as an alternative to working with states which are the following things. They are just column vector of n complex numbers. Okay, you take n complex number and you just define a column vector with n complex number. This object belongs to a space that is called Cn. It's the analog of Rn, the real space Rn, just n complex numbers, okay? And you can work with this as a vector space. This is a finite dimensional vector space. This is in principle an infinite dimensional vector space, okay? So this is in some sense easier to deal with. And I want you to familiarize with the concept that you can define elements in a space which are simply n numbers, n complex numbers. Okay? Yeah.
So the one you say is infinite is the side. Which one? Which one is infinite?
This is, generally speaking, infinite dimensional. Okay? This is n-dimensional. It's an n-dimensional linear vector space. This is an infinite dimensional linear vector space. Okay?
Is it like projecting to the n?
What?
Is it like from infinite to n-dimensional? It's like
Not from. Two different examples. Okay? When you exemplify things, I can give you one example, another example. Okay? There's no connection between these two things. One is functions, and I can guarantee that to express a function, you cannot expand it on a finite dimensional basis because the functions can vary in a crazy way. And you need an infinite dimensional basis to represent a function. While if I have n complex number, this is a well-known space which is called Cn, the analog of very familiar to you Rn. Okay? You use just n real numbers, and this is the coordinate of a point in larger space. Well, is it clear? Okay?
We're
No.
discussing a different thing between that.
Yes, there is a line here. Line. One example, second example. Okay? Good. So do not please. I'm using similar symbols, but these refer to totally different things. This is a function, this is a function, and I define the scalar product in this way. Okay? This is a column vector. The simplest element is two complex number. Okay, so phi1 and phi2. A two-dimensional complex C2. Okay? This is a simple example of a linear vector space, which I can certainly consider. Now, how do I define the scalar product for these things? You remember that for if these were real numbers, okay, and I ask you define the scalar product between, let's say, x and y, then you do sum over I from 1 to n of xi, yi, right? And therefore, xx is equal to sum over I xi squared, the Euclidean length squared. Yes. Very good. Now I want to do the same thing for complex. And the result is the following, the definition is the following. I take an element psi, an element phi, okay? I don't use phi1 and phi2 because I want to have the liberty of using this 1 to n for the components, okay? So I use two different symbols for the two different vectors in the space, okay? So this is equal to sum over, say, j from 1 to n of psi j star phi j, okay? The reason for this star here is that in this way, if I want, for instance, the phi element, this is equal to sum over j, or 1 to n, of phi j star phi j, but this is the modulus square of phi star. So this is a positive quantity, and this is the length of the norm, okay? If you don't put the star here, things are bad, because I have phi square, and phi is a complex number, not nice, okay? For real number, you need nothing. The square is enough. But for complex number, you better put the star here so that when I do phi, I get phi modulus square. Okay? And this is a reason, a very decent length. Okay? Is it clear? Okay? Good. So you see the difference between integrals and just sum of a number, a finite discrete number of elements. Okay? Good. Now we have these two examples in mind, an infinite dimensional and a finite dimensional example of a space with a scalar product. Okay? What the scalar product should do, okay? Let's see the properties that any scalar product should satisfy. Property A is that psi phi belongs to C. Okay? So it's a complex number. The scalar product of two elements in a linear complex vector space is a complex number. Good. Property B, this complex number is such that if I exchange the two elements, I get the star. Okay? This is my definition of a scalar product. It should give you a star. Okay? In such a way that phi is equal to its star. So it's a real quantity, for instance. Now the property which is very important is linearity. So phi C1 plus C2 okay? So if I take a linear combination with arbitrary constant C1 and C2, complex constant, of two states, two elements, two vectors, then the scalar product with psi is equal to C1 psi phi1 plus C2 psi phi2. Is it clear? Do not get confused by this phi1 and phi2. Okay, these are two elements, okay, which themselves, if I am looking, for instance, at this example, I should attach the components number. So in some sense, phi1 is phi11, phi1n. Okay? So sorry, but in principle, the indices proliferate a little bit. Okay? But no problem. Just think in a more abstract term, and these are elements in the space, okay? In this complex vector space. and I pretend that every time I have a linear combination, the scalar product is just a linear combination of the two scalar products. Is it clear? And the property B is that for any psi is not only real, okay? It is real because of B, but is also non-negative, and in fact, the equality only if the state psi is equal to the zero of the space. You know that every vector space, okay, has a zero, right? Now, what is a zero depends on the vector space. For instance, in this case, is the function that is equal to zero. In this case, is a column vector all full of zeros, okay? But every vector, linear vector space must have a zero, because if you multiply a vector by the number zero, you get everything zero everywhere. Is it clear? Good. Now, the only possibility that the scalar product of a vector itself is equal to zero is that the vector itself is equal to zero. All other vectors should have a scalar product with themselves that are greater than zero. Okay, so this is the generic situation. Is it clear?
Yes.
Good. So these are the four properties.
Also, Professor,
Yeah.
you mean the all components should be zero.
Yep.
And then I think the notation is like you mean zero capital to be clearer, because zero is scalar.
Oh, okay, if you want. Okay. But sometimes I don't use. Okay, let's put it. Sometimes I don't even use the cat. The mathematician wouldn't use the cat. They are, I mean, very cat looks fake. This is a vector in the space. Okay? Zero is a vector in the space. Obviously, what is this vector depends on the space. It's full of zeros. Okay? Let's eliminate the cats. Sometimes it's just not very painful. Okay. Now, from this property and this property, you notice that this is somehow linearity. If I pretend to have the linearity on the left, then I realize that I don't get quite linearity. I get C1 psi 1 plus C2 psi 2 phi, sorry, equal to, guess what? Using this two, you first get the star and you bring it there. Then you do the algebra of linearity, then you bring it back, and you get C1 star psi 1 phi plus C2 star psi 2 phi. Okay? So this is called antilinearity on the left. Okay? So the right is linear, the left is antilinear in the sense that it's almost linear, you get the star. Okay? Another important thing is that this allows you to define the norm of a vector, okay? Or the length of a vector. You define it in this way due to the fact that this is positive and is zero only for the zero vector. You define psi modulo square equal to the scalar product of the vector with itself. Okay? This is a real positive number. And therefore, the length of a vector is the square root of the scalar product of the vector with itself. Okay? Pretty much as you do in Rn, Euclidean norm. Okay? Very, very similar. Just extending the concept of scalar product. Is it clear so far? Okay. So these things again are general concepts which are applied to the scalar product. They apply to this scalar product for linear space of functions. They apply to this scalar product for Cn. And in fact to any linear complex space you can embed. Okay, now the norm and the scalar product satisfy two very important inequalities. Okay? The first is called Schwarz inequality. The Schwarz inequality. And it reads like this. If I take the scalar product of a vector with another vector, and I consider it square, that's less or equal to the norm of psi times the norm of phi. Okay? Which you could write as psi modulo square times phi modulo square. Okay? This is pretty much the generalization of the inequality that you know for the cosine. You take two vectors, I calculate a vector v1 and a vector v2, okay? And I calculate the square of this. You know that this is equal to essentially the length of v1 times the length of v2 times the cosine of the angle theta between the two vectors. I'm thinking of three-dimensional vectors, okay? So if I take the square of this is equal to the length of v1 square, the length of v2 square, times the cos square of the angle between the two, okay? So you see that the maximum value for this thing is certainly less than the length of v1 and length of v2, okay? The scalar product is always less than the product of the length of the two vectors. That's the meaning of this object, okay? It's true for any scalar product in general. There is also another inequality that is called the triangular inequality. And I first draw it, okay? If I have a vector phi and a vector psi, okay? Then this is the vector phi plus psi, okay? Then the length of the vector phi plus psi, which as you see I'm not writing with cats, these are only vectors in this space. The length of this is less or equal to the length of phi plus the length of psi. In other words, this is less than this plus this. Okay? This is the length of phi, and this is the length of psi. Okay? So the length of the sum is less than the length of the two sides of this triangle. The hypotenuse is less than. Okay? Is it clear? This is the reason why it is called triangular inequality. Good. Clear so far? Another concept which is very useful is the following. Is a linear independence. You know from your linear algebra, you know when elements are linearly independent. Suppose that I give you a set of vectors, some vectors phi j. Again, I fluctuate in my notation. I could add here the cat or not. These are elements, vector in the space. I say that they are linearly independent. Okay? If, and only if, which sometimes you write like this, if and only if, when you have sum over j, phi j equal to 0, this happens when all Cj are 0. So the only way to get a linear combination that sums to 0 is that all coefficients are equal to 0 if the elements are linearly independent. Okay? This is by definition. Remember that I could have three vectors, for instance, on the plane. They are not linearly independent. I can make a linear combination with non-zero coefficient which sum to 0. With two vectors, no. The only way to sum to 0, I have to have the two coefficients equal to 0 on the plane. Is it clear? Okay, good. So this is the concept of linear independent. Now, the concept of orthonormal. Orthonormal is the following. The set is said to be orthonormal if the scalar product of phi j prime with phi j is equal to the Commutator delta of j prime j. In other words, they are normalized to 1, each of them, and if you take 2 of them, their scalar product is 0. Okay? This is an orthonormal set. Is it clear? I'm doing for you a kind of brief refresh of linear algebra. In some sense, this is just linear algebra. Okay. Now, let's demystify a little bit. Sometimes you find in quantum mechanics the bra, okay, this object here. Let's make it a little bit more friendly, okay? To do it, I need to explain to you one little thing. Well, I erase these properties. Maybe that would be useful, but I don't know. Okay. I now define, so this is, it is the space of vector H, and I now define a functional on the space of vectors to the complex numbers. Okay, so I associate a number to a vector. Okay? These are called functionals. So essentially, a functional of some vector phi is equal to a complex number. Is it clear? This is an argument. Now, linear function, okay, so a function is linear if f, as you suspect, c1 phi1 plus c2 phi2 is equal to c1 f of phi1 plus c2 f of phi2. Is it clear? Okay? So a function is linear if when it acts on a linear combination, it produces for you just a linear combination of the two. Yeah?
What's the above?
Huh?
What's the f3 equals to?
Complex number. So this elements in C. You see that I have C here?
And then the H is the
What?
the Hilbert space.
Yes, the Hilbert space. Or the linear complex vector space of your tree. Okay? So a linear function is simply a linear function in some sense. So something that produces for you complex number, but it acts in a linear way. This should not be confused with linear operators. Okay? So linear operators, which we have worked so far, are not functionals. Because an operator, say A, okay, a linear operator, acts on the Hilbert space and produces results in the Hilbert space, not in the complex numbers. Okay, you see the difference? Okay? But the story is similar. So a linear operator is an operator such A applied to, say, C1 phi1 plus C2 phi2 is equal to C1 A phi1 plus C2 A phi2. Now, for operators, you sometimes, for instance here, you would omit the parentheses. It's pretty clear that it means operator applied to phi1, okay? Operator applied to phi2. Obviously, in this case, I have to use the parentheses to say the operator acts on this combination. Okay. Is it clear? Good. So linear functions or functionals and linear operator, they should not be confused. Now, the linear functionals, notice, you could regard them as a linear vector space. How do I make the set of all functionals, or suppose that I take the set of all linear functionals, can I think of them as a linear vector space? Yes. I have to define how the sum of two functional is defined, right? And that's not difficult. The sum of two functionals is defined in the following way. Functional 1 plus functional 2, okay? When acting on a state phi, it should produce a complex number, remember? What do you expect will be this complex number? Is equal to the action of F1 plus the action of F2, okay? And what about if I have a complex number times F1? Is this a linear function? Of course. It is a linear function whose application on phi1 produces alpha times phi1 applied to phi. You see the order of this parenthesis is just to highlight for you that this is the linear function alpha phi1 applied to phi produces phi1 phi, the complex number, times alpha. Okay? Very, very, very trivial things. Okay? So I'm telling you is that if I have linear functions, I can sum two of them and I can multiply a linear function by a constant, a complex constant. Therefore, they become a linear vector space. Is it clear? That's the only thing that I'm telling you.
So alpha is a complex constant.
Huh?
Alpha here is a complex constant.
Yes, alpha complex.
And phi is a function while f is functional.
Yes. Okay. Clear? So distinction between operators and functional. Functional can be made linear space because you can sum function. An example of a functional. Okay? You fix some psi and you consider the scalar product psi phi when phi belongs to the Hilbert space. This object provides to you a complex number. Remember, property A of the scalar product. Okay? So in some sense, the map phi going to psi phi, okay, is a map that sends an element in the Hilbert space into a complex number, and it does so in a linear fashion. You remember that if I have here C1 phi1 plus C2 phi2, the result is a linear combination. Property B, I forgot, of scalar product. Okay? So you have already seen a linear function. It's nothing but the scalar product with a fixed psi, which you decide. Okay? So in some sense, I might call this the linear function associated to psi acting on phi. Is it clear? So for every scalar product with an arbitrary fixed psi, I can produce to you a linear function, which is this phi psi. Is it clear? Now we have demystified a little bit the linear functionals. They are, think of them as scalar product with something. The something you decide. So there are infinitely many, obviously. Okay? You just change the psi, and there change the linear function. Okay? And now, I told you, you can think of them as scalar product. The question is, are there any linear functionals that are not of this form? The answer is no. There is a theorem, it is called Reed's theorem, that tells you the following. For every functional f that is a linear functional, then a state psi exists such that, okay, let me write it for you, such that phi applied to phi is equal to psi phi. In other words, such that this object coincides with the function of psi that I defined there. Okay? So this is the content of Reed's theorem. Reed's theorem. I'm writing to you in a simplified fashion. This holds for a space of functions, a very general result. Here it looks like almost a trivial thing. It is kind of trivial. Okay? So now you can, in some sense, see what this thing is telling you. The scalar product is like, when you think of it as applied on the phi, is like if there was a psi waiting for some vector to come there and to apply to it. Okay? So in some sense, you see that this phi psi is a bit like a bra waiting. Okay? It waits for what? For a vector that is coming, phi, you put it there, and you produce a number. Okay? So it's a producer of numbers, ready for vectors to come. Vectors are cats, they come to the right. This is the bra, okay, ready for go eat the cat and spit out a number. Is it clear? Good. So let's hope that this makes the concept of bra a bit less obscure. Okay? It's simply something waiting for some poor guy, a cat, coming and making together a complex number. And it's essentially a linear function, okay, by Reed's theorem. And you can sum them, obviously. I told you that linear function. So as I have the bra psi 1, I have also the bra psi 2, okay? And I can sum the two, which is the bra psi 1 plus psi 2. And I can multiply by a number, C1, C2. No problem, okay? Just remember, however, that when I do this thing, I get the stars, okay? So this is the rule. The stars have to come to the left. Okay?
This can only happen in the linear functional case, right?
Yes, I think that I have done here. Wait. Okay. There's a small thing that here I should check. Because here I see a star. So next time I start from here. I stop here now because I want to make sure that I tell you the right thing about the star present in this. Okay? So would this equal to C1, psi 1 plus C2 plus no, or there is a star? I think that there is a star, right?
Yeah.
Okay? And so this would suggest that when I do a combination, so let me start next time exactly from this point. It's an interesting point where to, in fact, stop. Okay? Yeah.
Will we discuss about the antilinear one? Because I think in quantum mechanics we also have antilinear operator.
They are important for doing time reversal. Since we will not, and it is a slightly more advanced topic. Okay? So I don't think if needed, we can devote an entire lecture, but later on to time reversal and to antilinear operators. But they are not particularly useful. I mean, not for ordinary usage. Okay? But this I'll clarify next time. Okay?
Sorry, but
Yeah.
f is a function or functional?
Which one?
F1.
These are functional. Okay? So this take a vector and produce a number. Precisely like a block takes a vector and produces a number. Okay? Is it clear?
By definition, f is a function.
Where?
The first one.
Well, yes, it is. Everything is a function. Depends on the space where you start from and the space where you end up. an operator is a function in some sense, operating with a vector and producing another vector. In a generalized sense, everything is a function, okay? But here we devote our attention to linear functions first, okay? And then the state that you get, the object that you point at, could be either a vector or a number. And this distinguishes for me linear operator from linear function, okay? So I'll do, next time we'll start with it, okay? Ciao, ciao, see you next time.